All right. Hello, everyone. Welcome. As you can see, our room is slowly getting emptier and emptier. This is always how it goes, but trust me, being here is valuable. I routinely saw that, the students I routinely saw did well. They were actually, the people I routinely saw were a good benchmark for me in terms of if I am preparing people well. The thought process being, if I give you all the right materials, if you are putting forth effort using the things I tell you to do, ideally that should mean that you're doing well in the class. Now, well is a relative term. That's something I do want to mention to you all. Well could be A, well could be B, C ideally is not well. It can be depending on circumstances and what other classes you're taking and all that kind of stuff. But an A or a B is kind of where you want to be. I don't know this for sure. So back when I was an undergrad, my knowledge was that like for internship, I kind of use this as a benchmark for engineering. I think Lockheed was looking for like a 3.4 GPA. I don't know if that's actually the number anymore, but I'm just going to say that that's the number. 3.4. And it doesn't really matter too much if you're above that, but if you're below that, that was kind of like as far as GPA is concerned. There's kind of a floor, but the ceiling, if you're above that, it doesn't change too much. So all that to say, this is a good opportunity. I may or may not have mentioned this to you all before. I think I didn't. So remember, 50% of the grade in this class is effort-based assignments, and then the other 50% is the tests. So effort-based assignments are the labs, the clickers, the professional development thing that I mentioned last time that hopefully you've done, the quizzes. You should basically be getting all those points. They're basically free points. If you're doing the things, you should get all those points. The exams are the other 50%. So through the magic of math, if you get the 50% effort, that means you only need 80% averages or above on exams to get an A in the class. That's how the math works out. If you want to be in the class, you only need to get above 60% averages or above on exams. And the logic here being, if you get an 80% or above on an exam, that shows mastery. That's to me what an A represents. A represents mastery. It represents that you have a solid understanding of this such that you can do the problems. You might make some mistakes here and there. No one's perfect, but you're solid. You know what you're doing. You're not going to get above an 80% if you don't know what you're doing. 60% or above means that you have a decent understanding, but there's some holes. And that's where the B comes in. You know stuff, but maybe you're missing some things here and there, or maybe you make some mistakes or whatever. Then 40% or above gets you a C, and that's where there's some decent holes, kind of like what a C represents. You still know some things. As crazy as it sounds, you will not get above a 40% on an exam unless you know some things. You'll be like, that sounds crazy. That sounds like random chance. Random chance will be much closer to 25%. Like it's one of the, if you all have been in enough STEM classes, I think at this point, that you've seen that the averages in STEM classes are not high. It's one of those, if you know it, you'll do well. If you don't know it, it's going to be bad. Like, not like 40% bad, like 25% bad. As evident by averages on exams, pretty normally being in the 60%, 50% kind of range. As crazy as that sounds, this is complex stuff. I'm measuring the process. And above a 60% for me is kind of, I'm happy with. So, all that to say, if you're doing the things, that should honestly result in you doing decent on the exams. Decent, again, is a range. Some people more, some people less. To that end, if you have not looked at the problem sets, you're running out of time. And that is my metric for, that's the things you should be practicing. If you've only done the quizzes, and if you've only done the problems in class, for the vast majority of people, that is not going to be sufficient practice. I can almost promise you. Some people might be, but I'm going to go ahead and say for most people, it's probably not. If you have not looked at them, at least open them up, and this will be a good self-check. Look through the problems, and if you're not sure how to do that problem, that's probably one you should do. That's also a good rule of thumb. So even if you haven't looked at it, at least look through it and see which ones you don't know how to do. And if you don't know how to do them, that's a good flag, because if that problem or something similar showed up on the exam, you won't know how to do it then either unless you learn now. So that's my motivation to you all. Tacked on to that is my office hours are steadily going to be getting more and more full. So like my one today, I had like 8 people, which is awesome. Monday didn't have as many people because Monday are less likely. So Monday's always a good one to go to. Just note I can only fit like 9-ish people. There's a chance it's 10 in my office. Which like, that's a lot of people. I have 400 students. So why do I mention this? Please do come visit me. Don't be demotivated to do that. But just note that if it does end up really crowded, if you do pop by, there's other resources like Tyler. How many people have come to your thing, Tyler?
0.
Look at how much space he has. Come visit, sincerely, the help room and stuff like that. It is so much more efficient to learn when you have someone that knows what you're doing. And this applies to almost anything. In football, I was chatting with someone recently. I'm not actually too much into sports, so just clarity on that. But they were talking about how pretty much anyone that does really well professionally, like quarterbacks and things like that, it's very likely they've received some kind of private help outside of the traditional things, because when you get directed advice from experts, and Tyler is an expert, it just improves things drastically. They can point out things you might not even realize. They can help you through things quicker. It's an efficiency thing. You will learn more and you'll learn quicker when you're working with someone that knows the stuff. You'll see that for yourself one day if you haven't already. When you learn to drive, you don't just get in the car with someone who's never driven before. All that jazz. So, great. That's my soapbox. Please, please, please do these things. No matter how much I say this, there will be a subset of people that don't look at the problem sets at all, and then the test one will be the major wake up. And yeah, that'll be the major, that's been my experience. I've taught, enough classes at this point that I've seen that, and it's pretty much always, if someone comes to me and says, the test didn't go well, first question, ask them, how much of the problem set did you go through? Generally, it's a little bit of it, some of it, and that's always the easy, okay, do more practice. It sounds rough, but that's the only way you get better at anything in life. All right, so to more fun things. You got the joke.
To whoever stole my cloning machine, I hope you can live with yourself. Thank you.
Could you clone yourself? Live with the clone of themselves that they stole. Great. It's good. That's the fun thing with these jokes. It's when they take a little bit. All right. So something I also want to point out to you, I love when people come to my office hours because it gives me feedback on what things are challenging. And so the things that are challenging are the things that I kind of mentioned before, specifically setting up the integrals and Gauss's law. They're the classics. Those are the two ones that I like Gauss's law, especially right now. So reminder to you all, this is the resource I point people to, the slideshow from last class. At the end of it for Gauss's, well, it's not last class. The Gauss's law, the most updated one. I have this slide somewhere on here. It's near the end. These 3 slides at the end of Gauss's law, I think, are extremely useful because when I am helping students solve these problems, these are the steps that I'm saying, do this, then do this, then do this, do this. This is the process. So first, when to use Gauss's law, great. And then there's the 2 guides. How to use Gauss's law? This is the recipe. Almost everything in life has a process for doing it, and this is the explicit process for doing that. But you trust me, just because this is here, if you just write this on your note card, but you never try it for yourself, it will go terrible for you. There's nuance to doing this, and you'll see what I mean. Try solving some Gauss's law problems, and this is the process. So use this, and the same thing we said on Coulomb's law. I have the slide on that. These are super, super, super useful in my opinion, based on when I work with students. This is literally the steps that I tell them to go through. Do this, then this, then this, and this. And eventually the goal is that you don't need to refer to the recipe to do it, that you know the process. Ideally, you also understand the reasons why, but that's obvious. That's harder. If I can at least get you doing it, that's great. One day, fingers crossed, you understand why. Another slide that's super, super helpful is this one, which is when you draw the Gaussian shapes, what they should look like. So when you do a line of charge, a rod of charge, you do a cylinder that encapsulates it at the point you care about. Plane of charge, you do a cylinder through it. Sphere of charge, you do a spherical. If you're not drawing picture, again, if you don't know the picture to draw, you're not going to get the problem. You're going to have no clue what to do. If you can't draw the picture, it's going to be awful. All right, so that's a reminder for you all. So today we're going to go through electrical potential energy, and we're going to actually get to learn about voltage, which is going to be great because voltage is incredibly useful. I'll do my best to convince you of such somewhere in here. And then we'll also get to capacitors, which I made the PowerPoints for those. Slowly but surely trying to get ahead of you all. I have the capacitors. So here's basically the last step I need to teach you all before the exam. So reminder to you all, your first exam is 2 weeks from this Thursday. It's a decent amount of time. Like it's a non-zero amount of time. So we're going to finish electrical potential energy and electric potential. They are two different things. I'm going to say that like 20 times today, probably more. Electrical potential energy and electric potential are two different things. So we're going to finish those up. And then Thursday, and today even, we're going to start on capacitors, and we'll finish up capacitors on Thursday. Fingers crossed, we'll have a lab on capacitors on Thursday. I have to still make that. It's going to happen. It's going to be awesome. So much fun. And then we might finish up capacitors the following Tuesday. We'll see timing-wise how that pans out. And then we'll talk a little bit about resistors with the chance that we'll talk about current, but that's dependent. So long story short, test 1 is going to be charges, electric forces, electric fields, electric potential energy, electric potential, capacitors, and resistors is kind of the topics. And those were mentioned before, but just to remind you all and give you a sense of how much left we have to cover. So, a lot of words, a lot of talking. Electric potential energy. If you all were cool with gravitational potential energy, same idea. Stored energy. Stored energy such that when you release the objects, they will do something. They will move. We chatted about it. We derived it. It was a grand time. Look, there it is from forces. So good. We did some problems on it. We did the plane one, and this one probably hurt people's heads a little bit. This was finding the velocity of a charge right before it hits the surface. You release it. The punchline here is that to find it, you had to do this integral of the electric field. That was kind of the skill, the main, and also that it's conservation of energy. Now we get into actually electric potential, which is great because, oh my gosh, it's so useful. It's so useful that every single one of you have seen it before, and it's written on every single electronic device you have somewhere. And 95% of people don't know anything about it other than it's written on batteries and stuff like that. So hopefully give you all, fingers crossed, a decent understanding of it. You all actually did a lab on it last time. So great. Okay. So let's actually get to it. So the question arises, what causes this energy? Remember before we said, what causes the force? And we made up a thing called a field. This is the question, what causes this energy? So we're going to do the exact same process that we did before. And when I wanted to find the field, I took the force and divided by charge. When I want to find what's causing this, I'm going to take the energy and divide it by the charge. That's how we're going to kind of define this. We say, hey, if I place some charge somewhere, it gets a certain amount of energy. Okay, why is it getting that energy? We make up this thing called potential. Notice that electrical potential, so that's, and again, I'm going to say this so many times today. Electric potential is going to be this V. Electric potential energy is going to be this U. They are not the same thing. One has the word energy in it and the other doesn't. One is energy, one is not energy. The energy is a symbol U, electric potential is a symbol V. We're going to have a nice slide showing it in a second. So don't worry, there's a cleaner slide defining this electric potential, but for now, just it's a symbol V. Don't get them mixed up. I know they are one word apart, but man, that's where everyone mixes them up. It happens. It will happen to you. So, with this in mind, that we're going to define this, that say if I put some charge there, how much energy would it have? So, I have some charge Q2. And this Q2 is making this hypothetical potential everywhere. And my question is, let's derive what it is. Let's derive the expression for the potential due to that, at some point due to that charge. How are we going to do that? We're going to pretend to put some other charge Q1 at some random spot, some distance away, and we're going to say to find the electric potential here, we got the equation for electric potential energy, and then we have the thing I just told you that V equals U over Q. And so the question is, what is the equation for potential at this point due to charge 2? What is the equation for the electric potential some distance r away due to charge 2? See if you can derive it. I believe in you. I'll open the question, pop it over to you. We've done this before, but instead before it was force and electric field. Now it's energy, yeah. I'll meander. Alright, I've done so much talking today. I know. You all as possible. I literally went to which is good. It was good. Look, I can't complain much because that was when I was in high school. That was every day. Right. I have sweet cake.
The creative rather it's the same thing as like the superposition whenever you're measuring actual line up with
So one makes a voltage, the other experiences. It's just like one charge makes it, like the other experiences. It's that same kind of loss. One makes it, one experiences.
You did already? Okay.
I know exactly. So that Q2 is like you could write it as Q2 with this Q1.
Yeah, that goes on YouTube. Some of the initial ones that was an issue in there. Okay, I'll go ahead.
It's gotta be C. It's gotta be C.
The only difference is at charge Q1.
because it was just
That's what I'm thinking.
Yeah, I would say
Wait, no, would it be P then?
Yeah, you should be.
No.
yeah. The final point to
That's what you decide on.
to the point charge.
Now, yeah, I'm like, so,
Yeah, because like, if you plug in,
it's defined by two.
right, that's weird.
Yes, this is potential made by charge.
Yeah.
Maybe I'm just reading this wrong.
I'm just trying. So we're just confused. Can you go back to the defined by the point charge to be the sources of the electric field. Is Q2 the one creating the electric field?
So that's what the question is asking. Yeah. What is it? Well, no.
Any like charge Q-tip, so we're assuming increase the electric field, increase
One makes it, one experiences it.
Yeah.
And so the one that makes it should probably show up. All right, what y'all want to do? All right, give y'all like 10 more seconds. Probably overkill.
It's just like this, right?
Yeah. And then what I also have to show people Q1 over what like keep the change. We'll often actually mess up the divisioning. Sometimes we'll take this and they'll chuck it up.
Oh, like multiply by it.
Yeah. All right. 5, 4, 3, 2, 1. All right. Whoever wants to do it. Who feels confident? All right. Tyler's gonna explain this one. And I'll chime in at the end.
I can never get this right. There we go. All right, so for this one, the basic idea behind it is that we need to think about which one is creating the electric potential and which one is experiencing it between Q1 and Q2. Since we are measuring here at Q1 and Q2 is the one kind of creating the electric potential around it, we would want Q2 to show up in that equation. So when we have here that V is equal to U over Q, we are measuring at Q1, and since V is K, Q1, Q2 over that, we can plug that in, divide by the Q1 here. And we'll get that the electric potential is equal to K, Q2 over R12, which is letter B.
All right, so I'm going to say the same thing I said. So you'll remember way back when we found the equation for the electric field, one makes the field, one experiences the field. Same logic here. One makes the potential, the other experiences the potential. And so the one making the potential should probably show up in the equation. If Q2 is making the electric potential, if we're saying what is the electric potential made by this charge Q2, it should probably show up in the equation. You know, someone contributes to a movie, they should show up in the credits. So there you go. Cool. And ta-da, we did it. So this is going to be a little mathy right now. So like I'll chat through this, we'll do the math, and then I'm going to explain the concept because I think the concept is far more useful even than the math. So what is this electric potential? Mathematically, it's defined as the change in potential energy experienced by a test charge with value 1C. So something makes this potential. If you pretended like you put a charge there, it would get an energy due to that. The variable in the units, this is like one of the only units that I'm familiar with that has the same variable and the same units. So the variable for it's V for voltage, and the unit's V for volts. And they're the same. It's like one of the only ones I can't even think of another one that follows this. It'd be nice if more of them did it, I guess. I don't know. And so you all just derived this one. So we derived that, so that shouldn't be anything too crazy. This one here, the one below this delta V equals delta U over Q. If you're like, whoa, where did this integral come from? If we go back some slides, remember that delta U is negative Q. Like this is just in the previous slide. It was the work done. This is literally the definition of work. The force times the distance. Q times E is the force. dr is the distance. We chatted about that before. And through the magic of plugging it in, integral of E dot dr, and there's a Q on the top and there's a Q on the bottom, and so they cancel. So if you're like, whoa, where did that integral come from? It came from the work definition. It's work. And we just get rid of the Q. Okay, so again, a lot of this right now, a lot of what I've just told you is a bunch of mathy things. Here's the mathematical way of solving it. Far more important than being able to do the math is for everyone in this is probably one of the most important things for me in this class, is at the end of the class, you have a conceptual understanding of what voltage is. because my gosh, you all interact with it literally every single day of your life. It's all over the place. No one knows how it is. So I'm going to spend some time now standing up, like trying to help you all build that. And we did it in our lab last time, so I'm going to be referencing that lab. This electric potential, another name for electric potential is voltage. Same exact thing. 2 words for the same thing. Why? Because I don't know why. There's just 2 words for the same thing. Voltage, electric potential. One, it's not electric potential. It's great. Think of it like height. Think of it like height. So, great. Here's my water bottle. How do I make it gain more gravitation potential energy? I moved it up. What did I change about it? It's height. How do I make a charge have more electric potential energy? I raise it to a higher voltage, a higher electrical potential. The higher, and specifically, and this is very, 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 very important, if this thing is located, gosh, let's, a mile in the air, but it's sitting on flat ground, is anything going to happen? No, I don't care how high up I am. If I'm on flat ground, nothing's going to happen. For it to actually fall, you need a high point and a low point. A ball is not going to roll if there's not a downhill. If there's not a lower point for it to go to, it's not going to go anywhere. Electric potential is the same thing. I don't care how high your voltage is, nothing's going to happen unless there's a low point. Those electric cables, the wires carrying electrical energy and all that stuff outside, carrying all the current and all that jazz, they're fine as they are. When do they become dangerous? Are you all concerned about them up there? Are you worried about them shocking you when they're way up there? Now, when they're grounded, so that you hear the word grounded, again, wow, they even use the same wording. Like, we define the ground and height. What's the height of the ground generally? Traditionally, 0. Guess what? In voltage, when we talk about grounding something, we call that 0 volts. So if you have something thousands of volts and something at 0 volts, that's a very, very steep hill, quote unquote. And so there's going to be a lot of moving charges. Those charges are going to go to that lower voltage very quickly. Technically, they go the other way. We'll worry about that in the future. But that's when it becomes dangerous. It's not when there's a high voltage. It's when there's a path from high voltage to low voltage. And if you are that path, it's not going to go well for you, just like if you're lying on a hill and a big ball rolls across you. Big boulder. It's not going to be great. So, all that to say, so you all did this lab last class where you all made almost like a map, a height of it. So I wanted to jump to this line. There's something called equipotential, which sounds like such a fancy word until you break it into pieces. Equal potential. That's literally what the word is, just a compound word. Equal potential lines. What is an equal potential line? It's a line where the electrical potential is equal everywhere on it. Wild. Why am I mentioning this? So let me go ahead and show you what one of these looks like. Again, right now I'm really just trying to help with the concept of voltage. So this little simulation, we kind of played with it in the past. You can put a charge, it makes an electric field. But what you can do is take this little thing, and when I hit this pencil, this green line here is an equipotential line. Sounds so fancy, right? Here's all it means. At this point that I took the measurement, my voltage is 9.686. If I move it literally anywhere on this green line, and if I'm really, really precise, it will also be 9.686. And if I move it to another place on that line, it's also 9.686. It's everywhere on that line. It's the same voltage, the same potential. All right, cool. So what? Why am I spending the time on this? Why am I harping on this? You all might have seen something called a topography map. It's a map showing mountains and valleys and things like that. We have a bunch of these lines. What do these lines represent? See if anyone knows how to read these maps. It's the different heights. Everywhere on one of those loops, the height is the same. So pick a loop and the height is the same everywhere on that line. Pick another line, it's a different height. Pick another line, it's a different height. You all might have seen these. So if I jump over to here, so here's an example of that, the height map. You kind of got a mountain. Everywhere there's a line represents how tall it is. The closer the lines are together, the higher the change, the quicker that it's changing, the steeper that thing. Charges do the same thing, but instead of a height, we have this electric potential. It's like the same thing. And again, I chatted with quite a few groups about this last lab. If I put a ball on this hill, actually, let's make it something that doesn't roll, just make life easier. What's it going to do? Slide down it. What direction is that net force going to be in? Hopefully everyone's cool with it's going to slide down the hill and the direction of the force is going to be along the surface. Guess what? In this equipotential, if I put a positive charge, it does the same thing. Which way will the force be? The net force? Down the hill. It's parallel to the hill. And the only difference here is if I had a negative, so this is positive mass. What we're going to learn then is if you had a negative charge, it's going to do the opposite. They'll go up the hill. Just like if we had a negative mass, it would slide up a hill, but we don't have negative mass. So if you all are cool with height, every time you all see the word voltage, think of height stuff. Take all the knowledge of a mass from your entire history of going up and down things and pretend like it's voltage instead. And pretend like instead of masses, it's charges. And if you can do this, then you can understand all of like voltage. And it's super. This is one of those things that I took, the same class as you all way back when. I didn't understand what voltage was until like my junior or senior year when I started teaching other people about voltage. And I had to actually think about it a bit more. So if you can understand what it is, oh my gosh, it's so much easier to understand everything in this class. You'll understand how electricity works so much better. An example of a battery. There's two terminals on the battery, positive and negative. Why? Nothing's going to happen if you don't have a high point and a low point. You need a high point and a low point. Otherwise, if it's all just high, if my height is the same everywhere, nothing happens. But by having so this 1.5 volt battery means that like this side is 1.5 volts and this side is 0. There's a difference. Nothing happens though until what do I need to do to actually make electricity flow? Connect them. If they're not connected, everywhere on this wire is 1.5 volts. It doesn't know that there's a low point until you connect it to the other end. And now the charges will start to go from the high to the low. And then this battery kind of acts like a ski lift that takes them kind of back up to that high voltage and then they go around and so on and so forth. So we'll spend more time chatting about that in the future. But I just want to mention to you now because that's, batteries are like the classic. So great. Voltage is a height. Let's actually, I'm going to do these ones eventually, the mathy ones, but just to get at the idea, just so we can stick in the concept. Here's a situation. I got a proton located at a place where the voltage is 0. What will the proton do in this situation? Above it is a place of positive 50 volts, and below it is a place of negative 50 volts. Will it stay where it's located? Will it move upwards with a steady speed? Will it move upwards with an increasing speed? Will it move downwards with a steady speed? Or will it move downwards with an increasing speed? Think of height. Think of these as different heights. What will happen?
Yeah, it's gonna fall from.
Yeah, and you roll ball down here.
He just showed us the battery.
Great, there's so many ways. The one I also say is how fast it goes right now. 0. A little bit later, it's moving. It had to get back.
Exactly. Actually, I don't even think about that.
Yeah, that's the other one. That's like an easy
That's
sell.
very succinct.
Also, think about it. As the radius gets smaller, you can just move it. What's the equation? Yeah. As it moves, as it moves, radius goes smaller. I'm thinking about it because he said the direction is yeah, with the proton. Yeah, yeah. An electron in a battery really goes from positive to negative. A proton would be the opposite. To go from negative.
Yeah, we're gonna go to, there's no air resistance or friction.
Oh wait, yeah.
Yeah, that's exactly disconnected. Exactly. Yep. Oh. Cool. It's a positive charge next.
You've the survey?
Which way the positive way we expect to go up. Great. Cool. Good. It's gonna go down. Why is it gonna Why? The force involved, yeah.
I think it is.
Sure. Yeah. The other
Increasing speed. 3 is changing. So no matter what, it's going to start.
0, and then it will. By definition, I'm going from 0 to anything.
We're deciding between C.
All right, 10 more seconds. All right, and 5, 4, 3, 2, 1. All right. So, is a proton going to go uphill or downhill? Downhill. Great. So it's going to go down. Steady speed or increasing? If you have a box going down a hill with no resistance, is it going to get faster and faster and faster and faster, or does it go the same speed the entire time forever and ever? Faster and faster and faster and faster. There is a force involved. The other example I give is right now, when you first release it, how fast is it going? 0. But then afterwards, it's not 0. It had to get faster to go from 0 to anything that's not 0. By definition, for you to start moving, you got to get faster. So yay, it's going to move downwards. Now, something really, really cool here. I didn't tell you what happens. I didn't tell you how quickly this happens. So like it could go really quick. It could go really slow. If you all remember from Physics 1, the really powerful thing about energy is if I have a box, I'm going to give you all 2 problems. In fact, I probably should make this a clicker. Here's one box. Here's the other box. And I say they both start at the same height. And they both end at the same height. How do their velocities compare? They're the same. You don't care about the path that you take. You don't care how wobbly that path is. You don't care how long that path is. You only care about my starting height and my ending height. That's why conservation of energy is so useful. Voltage is the same thing. The only thing you really care about, the only thing that'll be a problem is if there's a bump in the way. That's a higher voltage that you can't get over. But there isn't that. So, anywho, great. Great job, great job. I'm only going to give you all a minute for this one. I'll make sure you have time to read it. An electron is released from rest at the dot. What will the electron do? Will it remain at the dot? Will it move upwards at steady speed, move upwards at increasing speed, move downwards at steady speed, or move downwards at increasing speed? Give you all till minute 30. Way more time than you need.
You said the battery was like a school it has to be that it's being pulled. It's not having the electron goes from positive to zero. The battery, the lump, I just feel like 0, right?
Yes.
So let's use our height. What do y'all think?
I think it's
Okay. What do y'all think? Agree, disagree? Alright, we use our height analogy. A negative charge is like a negative mass. So positive mass would go down a hill, a negative mass would go.
But doesn't the battery get the electron?
Yeah, so when we talk about batteries, things get a little, there's a bit more details.
So we shouldn't use that as an analogy.
You can, but so what's going on, in the case of a battery, there's a chemical reaction. So I can think of a battery like a ski lift, is one way of thinking about it, where you're taking charges, and traditionally they want to go downhill, but the battery is a chemical reaction that drives them uphill. That drives them to a place that they normally wouldn't actually want to be. Just like a ski lift drives you up a hill, which you naturally, if you're standing above the hill, you're not just magically going to go up the hill. You got to have something giving you energy to move you up that hill. Chemical reactions are what's doing it. So in the case of a lithium-ion battery, literally positive lithium ions move from the negative terminal to the positive terminal when you recharge it. And then as when it's then being used, they transfer back. Yeah. Which is interesting. Yeah. That's good. All right. I gave you way too much time. All right. 5, 4, 3, 2, 1. Ka-chow. All right.
All right, so this time we've placed an electron at our dot, and so following the same idea, but because it's going to want to go towards that positive potential, we're going to say C, and justifying that it's with an increasing speed, again, following the same idea that essentially like the potential is going to change as it moves. Yeah, does that make sense?
Yeah,
Okay.
it's rolling down.
Yeah.
All right. So I'm going to also explain this to you all two different ways. There's so many ways to understand this. One is just this idea of height. That's one way of understanding it. Another, let's actually go back to energy. Remember I told you all, so in the last slide, I said that voltage is the change in energy over Q. Well, I can do the exact same. I can rearrange this and say that the energy at some place is the voltage times Q. So I want the energy at some place, I can do this. Why does this matter? Let's go ahead and find the energy at various places. So the energy here is equal to the charge of an electron. Is that positive or negative? Negative. So, and the voltage here is 0 and the charge is negative. So it here has 0 joules, quote unquote. Cool. Let's go above it. When we go above it, my potential here is 50, positive 50 times negative Q. Through the magic of multiplication and rearranging things, I get a negative voltage. Why does that matter? Negative, any number that's negative is smaller than 0. Negative 5, smaller than 0. Negative 10, smaller than 0. Negative 1,000,000, smaller than 0. Why does this matter? Everything in the universe wants to go to lower potential energy. It's one way of explaining everything in the universe. Everything wants to go to lower energy. So a negative charge is going to lower energy by going upwards because it's a negative charge, so it gives us that negative. Whereas when you're down here at the bottom, you have your voltage that's negative 50 times the negative charge, and so this is actually a higher energy for the electron. The negative sign flips everything. So this is one way. Another way of understanding this is the equation for voltage. Something very, very, very important here is there's no absolute value signs. And so this is relevant. I'm going to give you all another example. How high above the ground, if I set my ground as 0, how high above the ground is my water bottle right now? Roughly, in meters. I'll be kind. I'll make it even easier. It's like 1 meter. Positive or negative? What if instead I set the ceiling as my 0? Now what's the height of my water bottle? Negative 2. Height can be negative. Voltage can be negative. What does a negative voltage mean? It just means it's a smaller number than a positive voltage. That's all negative voltage means. It's all comparison. We only care about the change. So all that to say, what makes positive voltage? Positive charges, because there's a Q up here. So we can pretend like this positive voltage is made by a bunch of positive charges. What makes a negative charge or a negative voltage? Negative charges. So which way is an electron going to move? towards the positives, away from the negatives. So many. Everything connects together. Everything comes together. All right. Now, I keep jumping around because after teaching this morning, I realized I want to kind of talk about the concepts and then we'll do the math. So this problem, and this is going to help us segue into capacitors too. Which of the following would be the correct equal potential lines for two infinite parallel plates with equal but opposite charges? So there's a lot. So reminder to you all, if we go back to this slide, the closer the lines are together, the stronger the force. What causes this force? What causes the force between two charges? So difference in potential is one way, but what was the way we were chatting about it before? I have a charge placed somewhere, and it's experiencing an electric force. What did we say were what's the thing we made up to explain these electric forces? Electric fields. So why am I saying that? The closer these lines, the stronger the force. The stronger the force, the stronger the field. They all interconnect. So, the closer the lines, the stronger the field. That's kind of the end point I want y'all to get to. So, looking at this diagram of infinite planes, which of these accurately represents how the voltage is spread out? And the way you're going to answer that is you need to determine how the electric field varies within a capacitor. You might have to look up, and you're like, well, I don't know that. Look up the equation for the electric field due to an infinite plane and then multiply it by 2. And that'll be the electric field inside this. That'll give you an equation showing how it changes. Yeah, and we'll see how this goes.
Don't think about explaining that though. But I know it's like every amount we do for the right is decreases if it fixes, of course.
Stronger field.
Right.
Feels the same.
Right.
So they need to be equally spaced.
Yeah. That's what's so good.
Here would be a strong field, and it gets weaker. Here I have a really weak field, and it gets stronger. Strong, weak, strong.
Take away the constant field.
Oh, for the charge sensor.
Yeah, they are.
Yeah, so but yeah, that's this question. So, and this is then going to segue us into doing the integral.
Okay.
It's the opposite of the derivative. It's fine.
This right here has really high electric force. From all the way over here, there's no, right? It's all the way over here. The angle. Does that make sense? And then yeah, because it's a small angle. The farther you pull away, these take a greater vertical force.
But then why would they have to even if it's going to work this way? Because it would be like more lines or dollars and then more like strength. C displays this kind of thing versus D is like
Yeah, I think.
Alright, did y'all find the electric field due to an infinite plane? Alright, so as distance changes, how does that change it? So the electric field, sigma, does that depend upon distance? What is it? Yeah, just charge over area. It's just literally my charge density. That's a constant. Alright, sigma is a constant. 2. Epsilon naught. So how does my electric field change in the capacitor as I get farther away from the infinite plane? It's a constant everywhere. So y'all find my equation for the electric field to go infinite plane? Okay. What is it? Yeah, two of them would be, yeah, and then one of them would be over two, and two of them. All right. So as I get farther away from infinite plane, that's my electric field. Stay the same. Same everywhere inside. We're some distance away. Actually, countries are considerably really actually are. Yeah, and it all comes down to the electric field everywhere between those plates is identical. It's no, it's just point. It's making these infinite planes. Now, the reality is, no infinite planes exist. But if you take two sheets of paper and put a really close to each other, in between them is analogy if I put my face really close to the so that's what it's about. Yeah, that'll be the next step. Oh, that's not everything else follows that rule. Capacitor, infinite planes is the one thing we've looked at. They don't care about this thing. So the reason you're really close to the electric fields is going to be like super flat. They're bigger, but they're like flat. So the vertical components are much. But then when you get farther away, they kind of start rising smaller. But the vertical components contribute more. So you get to kind of like, it's kind of like if you get farther away from it, you can see more charges. And so you see more, so it makes stronger fields. Go farther away, so it makes a weaker field. They balance it out. All right, I'll give you all 20 more seconds. Just, again, I think it's when everyone's answered. All right, in 5, 4, 3, 2, 1. So this is going to be helpful, like for the future. It really all comes down to. So I told you all this equation here. This is the equation for the change in voltage, and this is where I kept telling you. So I told you conceptually why. Remember the steeper the hill, the stronger the field kind of thing. But mathematically, this is why. Mathematically, it's because of this integral. But something is special about electric fields due to infinite planes. If you have one infinite plane, it's over 2 epsilon naught. If you have two of them, then it's double that. It's a constant. The electric field is the same everywhere inside this thing. Infinite planes are weird in this way, but it's super, super useful for us as far as designing capacitors. So the electric field is a constant, meaning my lines should be spaced equally far apart. So the answer is D. The field is a constant, meaning my lines should be equally spaced from each other. It's a nice kind of graduate. And we'll see more slides about that in this capacitor stuff. But I figured since we were in this point, so nice work, nice work. This one here, C, would mean that my field is stronger closer to the plates and weaker in the middle. But the way infinite plates work, we did the math with Gauss's law, is that it's a constant everywhere. And the real quick explanation conceptually for why infinite planes are the same everywhere is you can almost imagine that when you get farther away from the infinite plane, you can almost imagine seeing more charges. And so you kind of get more charges contributing vertically. Whereas when you're really close, you can kind of only, quote unquote, see the ones that are close by. And so this idea of like you get farther away, so it gets weaker, but you see more charges, so it gets stronger. That's kind of a rough way of explaining why.
Would a pair of finite plates look like C?
A pair of finite plates would still look pretty similar. So fun enough, all capacitors, they're not infinite, shock and awe. But no, so this is a great, yeah. So the reason I mentioned this though is every capacitor is a finite plate. But if you imagine taking two sheets of paper and you put them a really close distance apart, that distance apart is so small compared to the size of the plates that they're effectively infinite. Now, that does raise a good question. On the edges, you get some weird stuff. We call those fringe effects. But the vast majority of it is constant. Yeah, that's a great question. So, all right. So now let's go ahead and actually do an integral problem. I kind of skipped this. So this is like the more trick. Like it's not going to be anything terrible. It says find the electric potential, some distance z above an infinite line of charge, With a uniform charge density, since the charge is extended to infinity, the potential won't be 0. So we're going to set the potential 0 at R naught. You're like, what the heck's going on here? Let me draw a picture. Pictures are always great. So what are we solving for? We are taking an infinite line of charge, and I am asking you to find the voltage at some point Z above the wire. Previously, we did this problem. We found the electric field at some point above the wire. So now I'm just saying, all right, great. We did electric field. Let's find voltage. And I'm going to show you there's a really, I just showed it to y'all. There's a way to go from electric field to voltage. And that's what we're going to do to solve this problem. So we're solving for voltage. How do we find, what's the relation? So we were like, oh, this looks like something, we found the electric field due to this. So how do we find this? Negative integral of E dot ds. That's the relationship between electric field and voltage. ds is the direction is like the path we're taking. And E is the electric field. So R naught, so Z is our final location. Remember I told you all, when we're finding voltage, it's always a difference. It's always a change in voltage. It's always, but if I asked you how high up this water bottle is, what would be like if I said, hey, how high up is this? What are you going to set as your reference? The ground. And what are you going to set that reference to? We're going to do the same thing here. When I say what's the potential here, I need to set a reference, and I need to set that reference to 0. Just like when I ask you how high up is something, I need to set a reference, and I need to set that reference to 0. So in this problem, I just say, pick a point R naught. I don't care. Look, we'll put it up here. What's special about this spot? What's special about this spot is that the voltage is 0 there. Why is that useful? We're going to take our hypothetical point. So we're going to integrate from that spot to where I end up. Now I will say, I'm actually going to fix this just to, because this is backwards of what we're going to find. And I want to avoid that complication. So we're going to start at some spot, and we're going to say that the potential is 0 there. That's our 0. Yeah, I'm going to let you all try this out. You all need to find the electric field due to an infinite line of charge. There is a dot product here, so I guess I'll be super kind and remind you all of this. Integral of R naught to Z. Remember, every dot product can be the magnitude of the first vector times the magnitude of the second vector times the angle between them. So you need to find the electric field due to this infinite line of charge. You all need to find the direction I'm moving, the direction of the field, what's the angle between them. Plug it on in, do the integral. It's a really easy integral. I'm not asking you to derive the equation for the electric field. Just find that somewhere. It should be somewhere in your notes. It's in the problem set. We did it before. If you're not sure what it is, Google it. And that's even the answer here. I actually had it flipped.
Yeah.
If you put R naught below it, I think that happens. No, it doesn't even happen. I think the answer is just wrong.
Yeah.
I don't know why it was flipped. It's something I
just forgot to put that there. I forgot of it. Check it out. I think it's
Okay.
X component.
It's a more effective search engine nowadays.
Yeah.
A really simple question.
Yeah, now you're making me second guess it.
Yeah.
You sure?
Come on.
Yeah, how do you get land in
Mm.
So,
There we are. Oh, that makes sense.
yeah, that's more so.
Did you learn
Yes.
the ASTC?
Is that for which one is
So like everything
positive?
positive here, sign positive here.
Yeah. Oh my god, that's long. Now I'm making a freak out.
I still use it. I'm trying to make sure.
Can you take a picture?
Oh, do you mind? I can take a
Yeah,
picture. You hear that? You missed that?
So in this case, it's a positive charge, so the electric field will point up. Which way are we going? Where do we start? Goes up, that's down. Yeah, so cosine 180 is. So that cancels out the negative. Yeah.
It's a distance
Yeah.
from your feet, like your target playing field
Yeah.
to your point.
And bring over the factor table. So DS is just an arbitrary.
So that, yeah,
DS
exactly.
says
That's
the
an R.
the direction of the so this, all this comes from the work equation.
Yeah,
and
exactly.
Where DL is the direction.
Okay.
Yeah, I mean, DS is an arbitrary path that we're going to utilize. It's just easier to understand. Yeah, and that's super common. We've been that. We're like CR, DS. It's an arbitrary path, and then we'll kind of change that to the actual. One of the funky things with motion is we keep it general, yes, and then in our problems we'll actually specify.
You don't between E and D, and you don't need to stuff
Yes. So let's do one at a time. Which way am I? Where am I moving from and to? So check out my downs, my angles. This is the initial.
Yeah. Not nice.
Starting.
Yeah. Because you're just your point and
Yeah, we're integrating over the path.
Oh, I see. Oh no, it's negative.
I didn't really have room to put it above, but I think the right spot. You actually put a big spot down here.
The outside.
It doesn't really matter because it is arbitrary. If you pick a spot down here, that's fine. It just results in I'll be more specific.
You're getting somewhere.
Right. It would be really cool if you this one is
yes.
the wire is
Where's the dog stand?
so just like And I set that reference point at 0. So this spot is some spots in the chart. That's why
Because the electric field's
says,
going
hey, here's our reference point. That's where I started, and I'm always going to start at
I thought we're going from. What is Yeah.
All right, so let's start,
Just like wave potential.
let's draw some pictures. So the electric field points up everywhere above this wire. We'll assume it's a positive charge. We can always just do that. Where do I start and where do I end? So E points up, DS points in the direction I'm moving. Where do I start at? Where's the beginning of my integral? My integral starts at R0. That's my initial to final. So I start here at the top and I move down. That's my DS. 1 point's up, 1 point's down. What's the angle between them? 180. What's cosine of 180? -1. Why is that useful? It cancels out our negative for us. All right, so great. We got that, while I'm in the business of plugging things in. What does the electric field do to an infinite wire? I did not expect you to derive this right now, though it is a good practice of Gauss's law and all that jazz. But I just told you to look it up. What's the equation for it? 2k lambda over r. You're like, whoa, where did that come from? We've derived it 2 times. It's a good practice. It's a great Gauss's law problem. We did it with coulombs. It's good stuff. I don't expect you to have this memorized. On the tests, I do not expect you all to have the equations for the electric field memorized due to certain geometries. I do expect you to be able to derive, not specifically these ones, but I expect you to know how to find the electric field to do a charge distribution. I expect you to know how to do Gauss's law, and those are the problems I'm going to have you do. If there was a problem like this, I would just straight up tell you, the electric field for something is this. Find the voltage at some point integrating from here to here. I wouldn't maybe say the word integrating, but I'd say, if the voltage was 0 at this spot and the electric field was this equation, find the voltage at this point. That's the kind of problem I'd give you. All right, so cool, negative integral R0 to Z, 2k lambda over R. Now, we're going to go ahead and also make some swaps. R, what direction is my thing moving? We're moving in the vertical direction. What's a nice variable for the vertical direction? So we're going to replace this R with a Y because we're going to measure things vertically. That also means, what's the direction of my path? That's also dy. R is an arbitrary, it's a variable representing the distance between things. Because we're talking about vertical distance, let's change it to y. ds is the path we're taking. What path am I taking? It's in the vertical direction. Change it to dy. This is something we're going to keep doing where you swap in the variables that's actually relevant when it comes to spatial. Did I start? Yes, but thank you for...
Somebody just messaged.
That's...
Said it hasn't started.
Should be there. I'll check in just a second.
Or
No, that's a good point. All right, so cool. This comes out to 2k. Oh, look, the negatives cancel. Yay. 2k lambda times the natural log of y evaluated from R0 to Z. And that is the answer. That is this. If you're like, what? How is it that? If you subtract 2 natural logs, it's the same as dividing them. That's the natural log rules are helpful to know. Just to write that out, natural log of Z minus natural log of R0 equals natural log of Z over R0. Why is that true? Because it's an identity that, honestly, I don't remember the derivation of. You don't need to know the derivation for it. Math. All right, so cool. All right, so did that. This is a nice little summary slide. Look at that, all the things. Change of potential is Q times delta V. It's always a difference. Point charge KQ over R. The integral form. Charges generate potentials. They get energy when placed in it. Yada, yada, yada. Fun things. All right, this one I'm not going to bother with because it's honestly more the same. All right. Wait, why did I make this? Nope. This is not a clicker question. All right. A proton is placed at the positive plate inside a parallel plate capacitor with a potential difference of 100 volts across them. How fast will it be going when it reaches the negative plate? I'll remind you, if I ever ask you how fast something is going in this class, there is a technique you should use. For test 1, it's almost guaranteed you're going to use this technique. I'm not going to tell you what the technique is, though. We used it previously, like at the very beginning. We've used it 2 times in the slideshow so far. One at the very beginning, one in the middle, and now we're going to use the technique here at the end. I'm going to check out my stream for it.
Somebody just messaged on web courses that they can't view it.
Yeah, it's because it's called lecture for some reason. I chose the wrong one.
Oh.
It's fine. It's still working. It's still
Should I
happening.
message them back?
Oh, it's fine. Yeah, you go to my YouTube channel.
User error then.
I have 14 people watching. Woo. It sounds like that. Or wait.
I feel like if it was the same part, it'd be the
Oh yeah. I won't respond.
And so my hint to you all, if you haven't realized the technique, I have a difference in height between 2 points, and I want to figure out how fast something's going to go when it reaches the bottom of the hill. What technique can I use to solve a problem where I give you the starting height, the final... You're like, you didn't give me the starting height and the final height. I gave you the difference between them. That's really all you need. Make the bottom 0, and you can tell me how tall the hill is now. I have a hill of height 100 volts. At the bottom of the hill, it's 0 volts. 100 minus 0 is 100. The potential difference is 100. How fast is it going at the bottom of the hill?
Because you're giving the potential difference.
Yeah.
no, because I have 1.6% range.
Because you
Specific kinetic before that.
Oh wait, no.
Well, not MGH, because we're not using gravitational. So,
Yes.
ours we got voltage equals energy and then we just use energy.
Did you take a square root?
Yeah.
Go to me would easier.
The right
Yeah, that's what I thought.
Yeah, I still ain't working for now.
You multiply by the charge if you want the
I'll double check.
point equals to the point multiplied by the charge. That point equals there. You want the difference? Is it 100 volts per 1 volt? So what's the cause? Or what do we even solve? Why do you divide it by 2? How fast we're going. And I told you the initial height of the hill, the bottom height of the hill. I said, how fast is the bottom? What's the What's the technique? Initial potential energy, initial kinetic energy.
Oh wait, look. Oh, shit.
Oh,
1.4. I mean, I got I didn't.
No, I got it.
Oh. No. No, it's not like 1 plus.
E to the minus technique. If I have a ball and the top of the middle,
I'm getting to the negative
Wait, but what if the mass gets a lot less? Because I have mass times.
it is conservation of energy. It's this.
Sorry.
Oh, you're good.
Am I like this setup? Do you think the mass is a lot or just
The potential energy is just like the opposite. We're just talking about the electric potential. Yeah.
So anytime I go off that, it's going to be conservation of energy. Test
10 to the minus 27. Can I see what you did?
It says bench difference. Bottom is 0, top is 100. 100 minus 0 is 100. What's the equation? How do I get to So it's the same way you go from field to say, just a small little thing you gotta do. Have the electric field, multiply by this. Have the voltage, multiply by this.
No matter what. It's scary now.
Don't worry, I'm never gonna have y'all do gradients. If that's any consolation, because gradients all partial derivative. Technically, it's a Calc 3 thing. So I mentioned it there just to show you that you can go. If you take the integral of something, you flip the opposite of that is taking the partial derivative. Have y'all figured this one out? Yeah, it's close. Yeah, that's good. That's good. Yep, it's rounded here. All right, so at this point, I've kind of written out all the pieces. I drew a picture of it because that's useful. It says the potential difference is 100 volts. Potential difference means the difference in potentials. That sounds stupid, but it's literally means subtract the two. So what I decided is to make the negative side 0 volts, and I decided to make the positive side 100 volts, such that 100 minus 0 is 100. It works. You could have made the positive side 1,000 volts and then made the negative sign 900 volts. And it would still get the same answer. So, you plug in these things. So my initial kinetic energy is 0. If I set the voltage at the end as, so, let's do this. Let's see. I want to think this through. Yeah, it's fine. So that means my initial potential is going to be Q times my V initial. This is one way of doing it, times Q times V final plus 1/2 MV squared. The way I set it up is I set my V final to 0 just to make my life easier. I'm allowed. And then the velocity final, I'm not even going to put numbers in because that's extra work. It's the square root of 2 times Q times the initial, which is 100, divided by the mass of a proton. You plug all that in and you get the answer. What's the charge of a proton? 1.6 times 10 to the minus 19. What's the mass of a proton? I think it's 9.11 times 10 to the minus 27. Or is it 1.67 times
1.67.
Yeah, I always mix them up. I know one's to the minus 27. I know one's to the minus 31. I know one's 1.67. Anywho. This is the benefit of working in variables. I don't need to know. Computer can do that. All right, great. So that's the answer. Conservation of energy. It's fantastic. So good. Yeah, and I mean this last slide is just showing you that, look, if you can do the integral, so remember that V equals the integral of E dot ds. So just get rid of the integral, so like take D, get rid of that, and you can write the electric field as the gradient. I only am showing this to you because, especially physics majors, this is going to be something very relevant to them. The electric, oh nice, there is physics majors in here. You're a rare breed. I think there's like 200 something physics majors in the whole university. There is thousands of engineering majors. So anywho, this is the, I always forget, divergence, partial, like, anyway, the change of the voltage gives you the electric field. How the voltage changes in space gives you the electric field. You're like, what? What does that mean? I've already said this in a different way. The quicker your voltage changes, the stronger your field. The steeper your hill, the stronger your field. It's the same thing, just written in math terms. That gradient, that's the partial derivative. It tells you how steep your slope is. It's a measure of slope, how steep it is. Steeper it is, stronger the field. I'm not actually going to have you all do this partial derivative or this gradient because it's technically a three-dimensional, like it's not a big deal, but it's a Calc 3 thing. Just to show you what this actually looks like. It's the, again, oh, stop it. Okay, well, my pen is being finicky, so maybe I won't show you. Yeah, awful. It's the partial derivative in the x direction times the x hat plus the partial derivative in the y times the y hat. Hey, it works now. So it is d dx in the x hat plus d dy in the y hat plus partial in the z hat times the voltage. Voltage is not a vector. So you take this voltage and you take the partial with respect to each variable, and that gives you a vector. And yeah, that's great. Super useful, but not necessary for this. So how do we create electric potential? I'm going to go ahead and leave this, and then after the break, we'll chat about it, and we'll explore one of the ways that we'll do it after that. Take a breather. Y'all got to like 3:30.
So we're doing capacitors.
Yeah, a whole big giant PowerPoint on capacitors. I'm even going to try to do series in parallel.
Nice.
Yeah. Every now and then, 2 mistakes can cancel, but it's pretty unlikely. No, that's totally good. I just happen to leave it as final minus initial. This is great. This is actually probably better. I did it the other way before, I so used to final height, initial height. So I wrote it in that form. This is probably better. But it's the exact same. Yep.
It was negative.
When you have problems? Yeah, so here's the thing, this change of potential. What's my final? What voltage do I aim for? Yep. Final is 0 minus, what do I start with?
Oh, okay.
Yeah. Right. So because we're going, and that's why there's a negative sign. The same is true of gravity. When something falls, it starts at a higher height, it ends at 0. So when we do final minus initial, it flips that way side.
Okay.
Yeah.
All right.
Yeah. So we ended a lower potential energy, so that final minus initial gets us negative, and the negatives cancel, and we get a positive work done. Yeah. That negative change of potential, that work is the negative change of potential. It is generally like, why is it negative? It's because you ended a lower potential. Positive work results in you ending at a negative potential. Yeah. If you just Google if you YouTube, go on Google and type my name, Wesley James, you'll find it there. Or you can go to the announcements and there's a link to it there. The easiest way is just type my name. You'll find my picture. They're all there. Yeah. Okay. Go for it. Whatever. Yeah. I'm not official. Yeah. Have a good one. Do you all know the first capacitor?
Like what it was?
Yeah.
I don't think I do.
I looked this up because I was like, I always want to start from
That's interesting. What was
Leyden jar. This is the first jar. It's not a Leyden jar, so it's literally just a glass jar with aluminum foil on the inside.
I've seen those made today actually. Because DIY electronic people, right? They always do that.
So that was the first. But it's one of those things that
I've seen it used for a Tesla Pro. The homemade ones.
it is it was the first rudimentary capacitor, and it can store some amount of charge. I don't know how much. I don't know if like a ton.
I think today, like my safe flash jar, my series of those, I think actually pretty large. I think so.
Okay, because I mean it's just
It's not the best, but
it's a pretty big distance. The glass is so if you think of the capacitor, absolutely not. The area is deep. The area is good. The distance is pretty large. I don't know the permittivity of glass.
oh yeah. Just because of metal inflation?
Yeah. I mean,
Schedule.
so I always compare this to my lecture class. And so my lecture class, I didn't finish this. That graduated half the time on Thursday because we did lab. But
Yeah, is your goal kind of like finish this on Thursday for a while?
it'd be cool if we could finish a lot of capacitors.
Is this just capacitor or is it?
My goal on Thursday is to finish everything about capacitors except series and parallel.
Okay. Gotcha.
Yeah. Ooh, that's pretty good.
Decent.
Yeah.
I've been working through all the problem sets.
Oh.
Trying to, for when somebody shows up.
Nice. I should probably do. Yeah. I very much sleep. I'll be able to figure it out. It tends to work. It did. So this one had. I don't know. Solution I got that didn't It's like R over Z.
Yeah, when I did it, I think I got mine backwards. But I just figured I could like set it up wrong. I think depending on the minus 58 equivalent.
Yeah. It's some negative sign thing. All right, so let's see. What ideas, how can we create electric potential? What do y'all think? What are some ideas that pop to mind? Go simple. Don't try to go any, you can go crazy if you want to, but like, whatever. Give me your thoughts. What do you got? Simple, complex, I don't care. All right. Since it's so quiet, you all chat about it some more, and I'm going to go around and ask people in smaller groups. That way they're less intimidated. And then I'll mention the ideas or something. How you all get build up your confidence through. What it is.
How would you charge? Just do two, give it one charge. time when it loses. How can we separate? The thing is,
And we have to have a charge on. How do we get a charge on? That's one way to do it. That's the first
I was like, oh my
How different
There's clearly a belt rubbing up against it. And at the top it's just got a metal coat.
Yeah,
Yeah, it's literally all those
no, I can take they can take your
industrial.
X and Y. Not Z.
Yeah, yeah, they are.
Do y'all have any ideas? How can I make this difference?
Oh, but no, you have a difference. What do you do? Mine looks like this.
Magic? No! Magic is an unexplained science. There's several times you all have made it. Yeah. You know what I'm saying? All these ones. Think of in your life, what things have. How do those work? Yeah, but what's inside of them?
So I can.
That's one way. The other way is you remember your first lap? Rods and rabbit fur. How did you set rabbit and turkey? Literally mechanical. Alright. Who's got some ideas? Now that you've had time to chat, and who's got some ideas? There's so many ways. There's three predominant ways.
Can you just create a difference in charges?
You can create a difference in charge, but then the follow-up is how. How can you do it? And there's a couple mechanisms that we can do it with. They're both things you're familiar with. One is a lab we did, and one is something that you definitely interact with all the time. Chemical is one. Chemical reaction is one way to separate charges. That's how batteries work. It's a chemical reaction inside of it. What's the chemical reaction? Depends on the battery. What's the other way you all can separate charges? You all did a lab on this. You did this. Yeah, static. You all literally rubbed a piece of cloth against a rod, and that's one way of doing it. You may be like, that's a... So, couple fun facts for you all. Did you know that your tires are conductive? Your tires on a car are conductive. This is very important. You know why? They are constantly rubbing on the ground. They would constantly be building up charge. If your tires were not conductive, they would build up a massive amount of static electricity on them. And so they have to be conductive to actually disperse that charge into the frame of your car and all that kind of stuff. Something you didn't think about. Another case of this, when you all get in the car in the winter, you're more likely to shock yourself because when it's drier air, you rub in your seat is cloth or whatever material, you'll end up shocking yourself more in the winter because the air is less. The last example is a Van de Graaff generator. That's that big fancy Tesla coil ball looking thing. Those things are so simple that you don't like, it's great. It's literally just a belt that rubs up against something on the bottom. It's just a belt going in a circle. On the bottom, it rubs up against I don't know what, some plastic or cloth or something like that. I forget the material. At the top, it's got a metal kind of comb. So it grabs the bottom, delivers it to the top, and it goes off on the metal comb and then goes to the sphere. A Van de Graaff, that big thing, is literally just an industrial way of rubbing things together to get charged. Anyway, there's one last mechanism. So Van de Graaff generator, that's the mechanical, literally rubbing. Battery is one. This was secretly there the whole time. Generators are the last one. We're not going to talk about how generators work until around test 2. Like before test 2, we have to learn about magnetic fields. But it turns out, I'll even just tell you all this. If you have a changing magnetic flux, it results in a effective voltage. You're like, magnetic flux, that sounds fancy. It's electric flux, but with the word magnet. Instead of electric field lines, it's magnetic field lines. And you just make the flux change. Whatever. We'll see that in the future. So, I saved this PowerPoint, and then we're going to go ahead and jump into capacitors. We're not going to get through all of capacitors today. It's very likely we're going to finish a little early today because I don't want to cram a million information in your mind. So, boom, boom. Save all these things before I forget, because I will forget. So if y'all go, there should be the PowerPoint slides posted for capacitors. Spent a bunch of time making it real pretty the last few days. So we're going to try to learn what capacitors are, how they're useful, the math and stuff behind them. It's going to actually be quite simple. In my opinion, this whole capacitors thing should be one of the easier topics we talk about. Interesting enough, capacitors are probably more engineering than physics. It's less about new physics. It's more about applying physics for a practical application. That is all engineering is taking physics concepts and doing something practical with it. Building a device, making some product. Whereas physics is all about just understanding the world. Engineering is about using that understanding to make useful devices that improve society. Both valuable. Engineers need physics to actually make new devices. If you don't know how things work, you can't make something cool. And physicists need engineers to make our phones. So, all that good stuff. All right, so capacitors. So yeah, what it is, its function. We're going to talk about all the things about a capacitor. Then at the very end, we're going to talk about series and parallel. We won't get to that till Thursday for sure. So, things you need to remember is stuff we covered this last week. The electric field for an infinite plane is E equals sigma over 2 epsilon naught. The relationship between potential and electric field is that integral to energy equals Q delta V. All of these are going to show up in some form or the other throughout this PowerPoint. All right, now, something interesting, I didn't know this because, so, I don't know, when I was making these, I always like to tell you all that, a little bit of the history, nothing crazy, but all right, this capacitor, where did they even come from? No one just went out and found a capacitor. There is technically a very, very large natural capacitor that you all have interacted with a lot. It's called storms. We'll chat about that briefly. Storm cloud on the ground just makes a giant capacitor. But the first actually practical one, this is just fun. You don't need to know any of this, but it's interesting. They were first invented in 1745-ish. 2 different people discovered it independently, which is always interesting when that happens. It happened with calculus as well, with Isaac Newton and then someone else. And I should know his name. I don't know if anyone knows it. It's someone from India, I believe. But that's an aside. Great. What's the purpose of this? It's the thing I just asked you all. How do we... Look, if we want to make circuits, we need to make a potential difference. How do we make a potential difference? How do we store these charges? If we charge them all up, how do we store them? This was the first quote-unquote capacitor. It's called a Leyden jar. It's very simple. It's literally a glass jar filled with water. And on the inner surface of that glass is foil, like aluminum foil or literally any metallic foil. I'm fairly certain it was aluminum, but I'm not sure. And then on the outside is more foil. And then you got this chain that reaches down so that you can kind of put some charge on this top part and it will transfer to this inner surface. Now, if you zoom in on just one side of this, I have 2 plates. 2 plates separated a distance apart. And they will have equal and opposite charge. They're effectively an infinite plane. Sure, it wraps around on the bottom, but who cares? If you zoom in a bunch, you can't, I can't zoom in forever. But you zoom in enough on that, and it's 2 infinite planes separated a distance d apart. What's the purpose of this? They store charge. Let them do experiments. You got to actually store charge if you want to experiment with charge. Wild idea, right? So this is the first kind of thing of that, and then they iterated from that. Capacitors are incredibly, incredibly important in our today's society, and they are literally the following. 2 infinite planes, and we're going to put an insulator between them. I'm not going to tell you why until the very end, why we put the insulator. Obviously, it's useful. We want to keep this charge separated. So an insulator is quite handy for keeping them separated. Otherwise, they're going to combine. If they touch each other, they're going to short. So we don't want that. So that's one reason for an insulator. But we're going to eventually learn this insulator also boosts the performance of the capacitor. We'll learn why eventually. We call this a dielectric. But yeah, fun fact, no one is making devices with infinite planes. Obvious, like hopefully that's obvious. They don't exist. Nor is people making devices with two big, giant, flat sheets of things. That takes up a lot of space. How do you make it take up less space? You roll it up. If you zoom in on this, it's still the same exact physics. At any one point, I got two planes that are parallel to each other. So through the magic of rolling it up, it takes up less space. So that's what most capacitors look like. I think I have a picture somewhere in here of what they actually look like in a circuit. Let's see. Is it way at the end? Is that it? No, that's not it. Oh, so sad. All right. Through the magic of Googling, I can find a picture. Capacitors. Here's what they look like functionally. They're a cylinder because it's an infinite plane. Not infinite, but it's two planes rolled up together. They take a variety of shapes. Some look like pancakes. I don't quite know what that one looks like inside, to be honest. But a lot of them are these cylinders. A fun practical example of this is your air conditioning unit. If your air conditioning unit, something breaks, one of the most common things is the capacitor. It's a big cylinder on the outside. It's about, I have no idea how to describe that size. It's about as far as your fingers can get, like, I don't know, 6 inches, and about maybe 2-3 inches in diameter, which imperial units I know. But it's there. If you all know how to measure the capacitance of this, then you can diagnose it and determine that's the part. You go to Ace Hardware, buy a new one, replace it, and you save yourself a few $100. Super useful. How do I know this? Because I replaced my own. Wow. It's really, really easy to do. But if you don't know about capacitors or anything like that, you're going to be confused or intimidated or all the above. So many uses of capacitors. So many. Again, this is going to be more engineering-y than physics-y, but that's fine. Stud finders. I'm going to show you an example of that way at the end of this PowerPoint. Car amplifiers use capacitors. Lightning. I put kind of. It totally is. Defibrillators, phone touchscreens, old-fashioned camera flashes, basic circuitry. Capacitors, their purpose is if you want a bunch of charge really quickly. A capacitor basically does that. You can almost think of a capacitor like filling a bucket with water. Your hose doesn't actually output that much water, but over time, you can fill up a big bucket, and then you can take that bucket and dump it. And that's a lot more water than your hose can provide. That's what a capacitor does for you. It stores up a bunch of charge, and when you need it quickly, you do this. So in the case of a car amplifier, when your music's playing, it needs different amounts of charge at various points. When you have like a lot of bass going, you need a lot at that moment. So they need a big capacitor in it to be able to store that and provide it when needed. Lightning is just literally the ground, which is often used as the term for zero voltage because it's a place of zero voltage. And you got some storm clouds that build up a bunch of charge. And oh my gosh, it's a bunch of infinite planes. It builds up a bunch of extra charge. Down here, it pushes away, or it attracts, I guess you could say. You know what? I'm going to do it the easier way because this is actually more accurate. It's a bunch of negative charges up here. They push away all the negative charges down here. And ta-da, we got two infinite planes. And eventually it gets so big that you get dielectric breakdown. We'll chat about that at the end. So many things. It's great. Defibrillators, they do the... Like, if you ever watching a show, they say, like, charging or something like that. It makes, like, makes that noise or whatever. And then they say clear, and then they hit someone with it. They're then just dumping all that charge into that person really, they're then making it flow through them very quickly. Great. Capacitors. Cool things. Super useful. Love them. So, we're going to start with the definition. Like, you're like, whoa, where did this come from? This is the definition of capacitance. Think of a word like capacity. That's literally where it comes from. How much charge can these things store? That's its capacitance. It's capacity. How much charge can I store per voltage applied? Because, more voltage, bigger voltage means I can store more charge. So we control for that voltage for this capacitance. So if I applied 1 volt difference, how much charge could I put on it? That's what this is. Capacity. Capacitance. The symbol is C. The unit is farad, named after some guy with the name Farad. Probably Faraday's probably, yep, it's probably definitely Faraday. Yeah, good point. Definitely Faraday. Yeah, we control for that. And again, the example you can use is, think of a tire. Obviously, if I put more pressure, I can get more air. Air in this case is like charge. Pressure is kind of like this voltage. So we divide by this voltage to give us a standardized. How much charge could I put on there per 1 volt applied? That's the idea. It's a base definition of it. It's not like derived from anything. And then we're just going to kind of go from here. This is kind of where we start here, and then we're going to take our physics equations and start plugging them into here. So yeah, I got a decent amount of clicker questions because the cool thing, we're going to derive it together. The equation for capacitance. Do know something that's interesting of note. A 1 farad capacitor is like huge, like that. I say huge, like that's a ton. A 1 farad capacitor is a big capacitor. More often, we're working with microfarads. So, for example, that big capacitor I mentioned for your air conditioning unit, that one is microfarads. Mine's 10 to the minus 6. That's more traditionally what you're working with. All right. So we already answered this, but let's see if you remember. We're going to derive the expression for it, which we already kind of did. What is the equation for the electric field due to an infinite plane? Is it sigma over 4 pi epsilon naught r squared, capital Q over 4 pi epsilon naught r squared, sigma over 2 epsilon naught, or sigma over epsilon naught? It's like, you can still make them, but that's a lot of charge that you can store on those things. No, it's something you would need a lot of charge for. Like, I honestly don't know. Micro, I know for the AC unit, but yeah, it's a good question. Ask ChatGPT. Yeah, and 1 coulomb is a ton of charge. Again, a lot of the problems we've been working with, we're talking micro. Yeah, how big is that? Yeah, that's just how much voltage you can put before things get dangerous. Because once you start so much charge, just like lightning, what happens when you get too much charge in the cloud? It finds a way. And the same will be happening. Okay. For the capacitor? Yeah, that's a heavy. I mean, yeah, check the dimensions on the one you all found. Did you answer the All right, that's either you know it or you don't. There's not much to say here. 5, 4, 3, 2, 1. Like, this is like, again, either you know it or you don't. It's sigma over 2 epsilon naught. Why? Because it is. Like Gauss's law, I think, wow, perfect. Good job. All right, I am not going to do the next one because it's, if I have 2 of them, then, it's twice as big. Great. But we're deriving things. All right, now I'm going to have you do this. The equation for voltage is negative integral I to f e dot dr. We just saw that. What is the potential difference between 2 infinite plates separated by a distance d, each carrying charge q and a, when moving from the negative to the positive plate? You all just told me the electric field. Put it in there. What am I integrating from? The left side to the right side. Call that here it's listed as dr. If I'm moving in the horizontal direction, what might we want to change that to? Try it out. You got this. This is where you get to put the pieces together.
Wait, it's D.
No, it doesn't matter.
Yeah, you want
Yeah.
Oh, yeah, we say.
It's the best way to make sure.
Yeah, or first.
That's a whole different. Yeah, you can define it.
It always makes me negative.
No, so I guess the question is
And then.
actually,
Yeah, because they're facing each other, so it's 180.
yeah.
I feel like I'm missing a very.
Well, what exactly is the the charge is for area. So it's just huge charge.
That's gonna, otherwise, if you don't do the integrals, according to this, the voltage difference half the integral. So we don't think this is something.
Between the two.
Nice.
Yeah.
Yeah. No, that's good. Yeah, you plug in the thing, you put the dx, you put cosine theta. You would just then need to draw the direction. So the angle between what two points.
Yeah, I was trying to figure that
Yeah, yeah. So which way is the electron move? So things go
Yeah.
Yeah.
What's the direction of the
So, is it the? Wait, is it cosine y? I just read that from a readout.
Is it pointing away from
I
positive?
I don't think so.
No, wait.
Yep.
It is negative on the
This
left.
way.
So yeah,
Which
you
way am I
have the
integrating?
negative before.
Where am I starting? Where am I ending?
So you're going to the left. Your D points.
Well, E points to the left too, right?
Check the last.
The electric field.
Oh,
So if I define the left to be 0, then I can cancel the negatives, right?
yeah.
Okay. Yeah, I'll do that.
Oh, it's gonna be very handy. Cosine 180 is gonna get rid of our negative sign.
That's what he's saying. Alright, I was trying to say cosine 180, so.
Yeah, yeah, just
All right.
negative.
Nice. Yeah, don't forget that. So we should start putting Q over A.
Okay, no.
Got it?
Yep. But because there's two of them. Yep. So boom. Plug that on in. And then we look at the other piece. Where am I starting? Where am I ending? Just Q over A. What are my bounds? Straight, yeah, so where it's convenient to position wise, I'd like to say we start.
You want that to be the variable?
Hey, yep, that's my bounds. Because we're integrating over a package. We start on the left, and so we can also the next one, you can change CR into X.
Yeah, you can put over.
Last thing you have to do is get like cosine of 180. Yeah, cosine of theta. Where theta corresponds to X between 1 and 2 things. Whenever you do a dot product, that cosine is between the two vectors that make opposites. So which way does the electron go?
Yeah.
So it's pointing away from the positive charges.
No, the integral space.
Yeah.
So they're going to point up, down, left, right.
Electric
The electric field points left. So which way am I moving? Right. So it's the angle between those. And then you just chunk it all in and do the integral. Yeah. Yep. Nice and easy. Yeah. Yeah, so the integral is super easy.
I was thinking you pull it out.
Yes.
Let's see here.
And that is literally the definition of capacitance. So they derived it. Yeah. Nice that you can do that. All right, give y'all like a minute more. Okay. Let's start with the logic. The logic is going to help you understand. Alright, so cool, you got your integral. What's the electric field using two infinite planes? Not solid. Why do you change dr to dx?
I'm going across here.
Yeah. Why did you set your bounds at 0 to
Going from 0 to
Sure.
some distance.
Yes, we know what's in your reference. This is going to be a different term too. So even if you made this like 2, 3, the math all works out. You don't care, yeah. You only care about the difference. It's all relative. 3, 2, 1, 2. Yep. And then integrating dx, go to 180, get rid of the negative sign, and you derive the expression for capacitance. Yeah, that's the next slide. Yep.
You know why? No, we don't need the same. Just get the slide. What is fraud over song to show how Oh, that's what you guys did. Yes, that's how we started. We're trying to solve that thing. I mean, you just said that we were doing
Yeah. The more you try to do it in your head, the more like it's not going to go good. Yeah. All right. Yeah. Sigma? Yes. It's over 2. For 1 infinite plane, it's over 2. For 2 infinite planes, you multiply by 2.
Where did you guys go?
The 2 comes from the other top bit at the bottom. Cylinder. Infinite plane, 1 infinite plane, over 2. 2 will double it. All right, 5, 4, 3, 2, 1. Again, what's super cool here is you're deriving the expression for capacitance, and it's just doing this integral. Delta V equals negative integral of E dot dr. We write this integral as the negative absolute value of E, absolute value of dr, times cosine theta. Okay, if you need to then pick, instead of dr, what are we probably going to write? Dx, great. Instead of the electric, what's my electric field? Sigma over epsilon naught, dx. This angle, my electric field points to the left. I am moving to the right. Therefore, this angle is 180. That makes a negative sign. Oh, that's convenient. Cancels out that negative sign. Where do I start? Where do I end? Start here, end here. Start at 0, end at D, and through the magic of integration. Oh, so I guess I'll write it out. This is going to be sigma times D over epsilon naught. And then you're like, that's none of the answers. Because you need to remember what the definition of sigma is. Remember that sigma is Q over A. That is the definition of surface charge density. And through the magic of plugging that in, this is the equation for capacitance. So, how much charge can I store on a plate? So, yeah, how much charge can I store on a plate? So, sorry, this isn't the definition of capacitance. This is the definition of voltage. But, very simple, now that you've done this, remember the definition of capacitance? Capacitance was Q over delta V. You all just found delta V through the magic of plugging it in. So remember, you all just found this, QD over A epsilon naught. Through the magic of plugging it in. The Q's cancel, and things get flipped. And ta-da! This is the equation for capacitance. Epsilon naught A over D. Just a couple steps. So how do I determine my ability to store charge, my capacity to store charge? Just think through the logic here. The bigger my plates, the more charge I can store. Bigger the bucket, the more water I can put in it. The closer my plates are together, the more charge I can store. Because then, they're going to be interacting a bit more. As charge builds up on one, it's going to push out the charge in the other, and they're going to kind of be able to stick more on there. The electric field is a constant, but our voltage was not. That's something to keep in mind. Electric field was a constant, but our potential was not. All right, so now we'll just do kind of a few questions. Yeah, I'm not too worried about getting through a ton more things, so we'll do a few questions. Yeah. That is a great question. The plates are the same area, and the plates get the same charge Q, just equal but opposite. One plate gets positive Q, one plate gets negative Q. Yes, these plates need to be the same area, otherwise we have an infinite plane and then one that's not infinite, for example. That'd be kind of weird. And yeah, that's all a capacitor is. It's very simple. It's literally two conductors with a insulator sandwich between them rolled up. Just a sandwich. So easy to make. All right, let's see if this makes sense. It's always good when we see a new equation to try out what happens when we change things. What happens to the capacitance if we half the distance but double the surface area? Will the capacitance stay the same, half, double, or quadruple? Slides are... So after this, we'll have about
the next
the voltage, yeah. So it gets to the heart of why does it have the voltage? Something. These just store it. They don't.
Yeah.
So you were looking at
It's to protect the stick.
All right, 10 more seconds. All right, in 5, 4, 3, 2, 1. So problems like these are ones I like to put. There will probably be at least one, if not more, of these questions as a multiple choice of, hey, what happens to this if I change this? Be prepared for these types of questions.
All right, so for this one, we're going to just remember that the equation for capacitance is C equal to epsilon naught times the area divided by the distance. So we can call this the initial capacitance here and say that when we change the values, we're going to get, we have double the area over 1/2 of the distance. We can pull this out. The 2 is going to be multiplied by a 2 because we're dividing by 1/2. And we're going to have that 4 times epsilon naught times the area over the distance, which is just 4 times the original capacitance. So in total, it quadruples.
That's it. Yeah, so the kind of trickier versions of this is I might say, I want to make a capacitor that has 4 times the capacitance. If I double the area, what do I need to do to the distance to make that happen? In which case, you rearrange this to solve for the thing that you want. So in that case, it'd be like, what happens to the distance? You solve for d, and you do the exact same process. Whatever variable you care about, in this case, I cared about what happens to capacitance, get that by itself. If I cared about what happens to the area, get that by itself. If I care about what happens to the distance, get that by itself. And then plug in all the changes, pull them on out. Great, capacitance, its ability to store charge. Now, how do we get this charge in a capacitor? We hook it up to some voltage difference. Some voltage difference. Now, this voltage difference could be a battery. It could be anything where I have a high voltage and a low, some potential difference between the two ends. So this little simulation thing, as we work with circuits, I'm going to be using this FET circuit builder thing a good amount. It's great. And so what's nice here is, you can have a battery, and then I can have a resist. I need a resistor, otherwise this is going to happen way too quickly. So I'm going to charge this capacitor. If you're like, what's a resistor? Great question. We'll learn about that hopefully next week. Future things. So anywho, you hook it on up. Now notice, nothing happens when only one end is hooked up because there's no height difference. You need both sides. You need a potential difference. Everything right now is just getting 0 volts, 0 volts, 0 volts, 0 volts, 0 volts, 0 volts, 0 volts everywhere. It's flat ground. Nothing happens. Now, if I then connect this, still nothing's going to happen because I opened the switch on purpose. So still there's that gap. So everything on this side is that high voltage. Everything on this side is the low voltage, but they don't see each other. Through the magic of closed action, I'm going to make this resistance super high so that this happens slower. Great. It will slowly start building up with charge. One side gets a bunch of positive, one side gets a bunch of negative, and eventually it kind of peters out. And great, there you go. So that's the idea of here charging it. Now, to that end, if I jump back here, what's very important, and actually we'll show this here. Oh, it's a bummer that I have the resistor here. Goodbye, resistor. Boom. All right. This battery, it's 9 volts. That means that this positive is 9. This negative is 0. Keep it simple. Everywhere here is 9. Everywhere here is 0. So what's the voltage across my capacitor if one side is 9 and one side is 0? It's 9. It's the exact same as the battery. If it's the only thing in the circuit, it's going to get the same voltage as the battery. Why? Because why did it get charged in the first place? Think of it pressure-wise. If you have two systems connected together, they're going to have the same pressure. Whatever pressure is used to inflate the balloon is the pressure being applied to it. It's kind of the idea if we use a pressure analogy instead. So, let's see if this makes sense. Two capacitor plates separated by a distance d are connected to a battery with a potential difference V naught. If the plate separation doubles while still connected to the same battery, what is the new potential difference? Is it 1/2 the original? Is it the original? Is it 2 times the original? Or 4 times the original?
I'm pretty sure it's the same. Yeah. Right. Yeah, like you can have them. Just capacitance that lower, right?
So everything else will change. So that's going to be quite a few problems about that. If I change this, I'm going to have like all three scenarios. What's a scenario where voltage stays the same? What's a scenario where charge stays the same? What's a scenario where capacity stays the same? It's how all these things interact with each other. What do y'all think? Still connected to the battery. Originally got the voltage from the battery. Yeah. All right, 30 more seconds.
I'm just curious for this scenario because I know I was also debating this, right?
Yeah.
We have that formula.
Sure.
Why don't we use that here?
Yeah, so that one assumes that my charge is still the same.
Okay.
So if you look at the previous voltage equation, Q over A. So what's going to happen here is your charge will yeah, so this gets to the heart of why does it capacitor get the voltage it does? Because it's next to the battery, that's what's separate.
Got it.
It's like the voltage in the battery. The capacitor's total charge is going to be
It's more so
because the capacitor can only charge how much the battery has. But the capacitor can only charge how much the battery has. But the capacitor can only charge yeah.
If I change this, so I removed, so we're going to learn eventually to see first we have our test one. The resistance with the every time you go across
Right now.
So C equals Q over E. Rearrange that for B. Resistance drops by
0% chance of getting it right.
Yeah, but they each kind of lower it until you get back to the bottom of the battery, then you're at 0, go back up, and then you just keep kind of going around the circuit. Each element drops it, so you're at the bottom, and the battery takes it back up, and around, and around. All right, 5, 4, 3, 2, 1. So this problem gets to the heart of why does this capacitor have a voltage at all on it? So I got some battery. So if this is a 9-volt battery, that means this side's 9 volts, this side's 0 volts. Everywhere here is 9 volts. Everywhere here is 0. Meaning, what's my voltage drop across my capacitor? 9 minus 0. Who cares if I separate the plates? That doesn't change that the difference is 9 minus 0. So this gets to the idea of what determines the voltage in a circuit. If you're connected to a battery, you're going to get the voltage of that battery. That's the idea. So that's what this is stressing. If I disconnected it from the battery, whole different story. Don't worry, I'll give you each of those. So there you go. After it's been closed long enough, if it's the only thing in the circuit, this is going to be an important idea. If it's the only thing in the circuit, it gets the same as voltage of the battery. Why? Because wires don't change voltage. Wires don't change voltage. So the voltage here, again, if this is a 9-volt battery, everywhere on the top is 9, everywhere on the bottom is 0. Then I got 9 on the top, 0 on the bottom. 9 minus 0 is still 9. Think of these like heights. And when I go across the capacitor, then it drops. All right. I got 3 last questions, and then we're going to call it good for today. So this is getting to the heart of what stays constant and when. So we're going to go through each scenario. What stays constant if I charge a capacitor with a battery, I disconnect it from the battery, and then I double the distance between the plates? What's going to stay constant? Will it be the charge? Will it be the voltage? Or will it be the capacitance? Only one of these is going to stay the same, and the other two will change. So this is not the same scenario. This one, I disconnected it from the battery, and then I doubled the distance. They can't go anywhere. Yeah, so these are kind of tricky, but they get to the. Capacitors are a weird thing. Like all circuits, it's kind of very interesting. Yeah.
The capacitor may charge when you disconnect the battery. The voltage drops. You know, and the capacitance is increased. Increase the distance. So when the other charge changes, it stays constant. Does that make sense? Because you increase the distance, the capacitance increases, the charge drops because you disconnect the battery. I mean, the voltage drops. Any voltage here, the charge is remains the same because it's raised to 9 volts if you had the battery.
So you charge a capacitor, No reason. I just pulled it out of the circuit, and then I put this plate and I separate it.
I was doing a lot more.
I charge it on up, so I charge the capacitor. I then take it out of the circuit, disconnect it from the circuit. I then take the plates of the capacitor, and I make them farther apart. What stays constant? At the what stays constant? From when I disconnect it. From when I disconnect it, I fully charge it, then I disconnect it, then I double the distance. What stays the same from when I disconnect it to when I double it?
I mean, I disconnected the battery.
That's a good question. What happens when I bring a charge through your wall? What happens to the charges in that wall?
Oh, they all move. So all the positives go on that plate.
So when you build up one's negative, it pushes away the negatives.
And was that Richard?
Oh yeah, and some plates only push it. Yeah.
And then how do you reset it?
Right. You connect the two ends together. Yeah, that's one way to do it. And anytime you work with capacitors, you should discharge it before. So like the AC unit, you better discharge that capacitor before you do any. Sure, you can turn off all your breakers. That thing might have some charge on it. You just take a little piece of metal and you connect the two leads.
Oh, if you're touching metal.
They're fine. It's preferential to go to the other side. So the flow is going to be the flow based resistance. To a metal bar is much better than you. You are way less of a good capacitor. All right, close this out in 5, 4, 3, 2, 1. So I'm going to draw a pretty picture of this, and that's going to help us see what happens. In fact, can I actually do it using the simulation? Oh, I can do it using the simulation. Can I zoom in? Oh, I can't zoom in. Darn it. All right, whatever. I'll draw it, I guess. It's not going to be as pretty.
Oh, wait, you can zoom in in the bottom corner.
I clicked it, and it was it was grayed out. I know. Yeah, it was... Wait, do the magic... There we go. All right, so I charge my capacitor. I then disconnect it. Boop. Boop. And then I double the distance. Now, so one of the things to keep in mind, there is something called capacitance that is epsilon naught A over D. That is the equation for capacitance. These are the things that affect capacitance. If I change any of these values, it changes capacitance. Guaranteed. If I change the area, I've changed capacitance. If I've changed the distance, I've changed the capacitance. I've changed the distance, so I changed the capacitance. So my capacitance here is going to be halved. my new capacitance is going to be 1/2 the original because the distance is doubled. So why do I mention that? Through the power of having this, it actually does move the plates farther apart. But something I want to point out, what do you all notice about the charges on there? Yeah, they stay the same because where are they going to go? They got nowhere to go. They're stuck. They are stuck on those plates. There is no escape for them. This does raise a good point that someone actually mentioned, and I want to remind you all. I mentioned this to y'all. If you ever work on electronics and there's a capacitor involved, so if at home the AC unit, say you do change that capacitor, even if you turn off all your breakers and everything, you're like, oh great, I'm safe. Always discharge a capacitor before you do anything with it. Just because you disconnect a capacitor from a circuit doesn't mean it's safe to touch. It's got a bunch of charge on it. How do you discharge a capacitor? You just take like a piece of metal and you touch the two ends of it. There'll be like two probes that So, for example, I'll just show you what an AC capacitor looks like. There's literally these prongs sticking at the top. So this is the one you buy from Ace or Home Depot. Just connect a thing between them. Make sure you touch all these together so that you discharge it. Otherwise, it may discharge through you, and that might not be a pleasant experience. So, yeah, long story short, though, what stays the same? Charge. You filled some bucket, and then you put it in another bigger bucket. You still got the same amount of water. Kind of thing. That's the idea. All right, that's one. Let's see how this went. Ooh, that's actually pretty good. All right, what stays constant? All right, we already did this one. If I leave it connected to a battery, what stays the same? Voltage. Great. What stays constant? If I charge a capacitor with a battery, disconnect the battery, use the capacitor, light up a light bulb, and then I chuck it across the room. But I don't damage the capacitor. Is it charge, voltage, or capacitance? It was the exact same one we had. I have a capacitor connected to a battery. I disconnect it, but I don't. All right, give y'all 20 more seconds. You buy a capacitor from somewhere else, or what you check out the same capacity. Whether or not China, India, America, no matter what happens to it, it better have the capacitance listed on that capacitor.
The voltage doesn't just like the voltage changes.
Because you charge it and discharge it. Right? Charge. All right, 5, 4, 3, 2, 1.
All right. For this one, you charged up the capacitor, so like we saw in the picture before, it got a whole bunch of positives and negatives all over it, and then you used it to light up a light bulb. So all of that charge left. The voltage also decreased then. And that means that the capacitance has stayed the same because you can just reuse this capacitor, an infinite amount of times, theoretically. But yeah, capacitance should always stay the same.
You all go to the store and buy a capacitor. You don't care what path it took to get to that store. You don't care if it came from India, China, America. If it says 5.6 microfarads, it better be a 5.6 microfarad capacitor. So regardless of what you do with this capacitor, as long as you don't destroy it, its capacitance should stay the same. You're never going to be going into a capacitor and changing its capacitance anyway, but whatever. So cool, great, awesome. There's a little cheat sheet for maybe, sort of, nope, we'll get to that. All right, so that's the last thing. Next class, we'll talk about the energy. We'll do an integral to derive it. It's really simple integral. And then we'll do series and parallel, and fingers crossed, be able to do a lab on capacitors and actually measure the charge stored. We'll see, fingers crossed, I can make all that happen.